In this module, we will start to discuss about an integral method that was developed in this part of this course, but for a problem that are very closely related to the electronics cooling or any PCB thermal management. In PCBs, you will encounter situations where if this is your PCB, then there will be regions where the heat source is not mounted and it is immediately at the entrance, but it is mounted a little away. So, this section can be treated as an adiabatic section, and then there will be multiples of these. So, however, we can look at this case of multiple heat sources later, but for the present situation we will first take the first step, which is to analyzing these problems using the unheated starting length, and it leads to a very interesting result, and that starts to give more confidence into building what heat transfer coefficient to use in the discussions that follows. So, this is the type of problem that you would have encountered, is that there is a flat plate and there is a thermal boundary layer growth if the Prandtl number is less than 1 and the thermal boundary layer is less in thickness compared to the velocity boundary layer. Here what we are doing is that we are shifting the heat source towards the right, and the initial region is the adiabatic region. Here if the flow is entering at some ambient temperature of T naught, this adiabatic region being heat flux is 0. So, T over that region is also T naught, and however, here a temperature, the temperature rises to a step function, that is T wall. If this is x, this is my temperature, and this is T naught, and this is T w. So, the temperature rises to a certain value and it is held constant. So, that is the isothermal condition, and so you have for x greater than x naught, if this distance is x naught, if x greater than x naught is T equal to T w. For x less than x naught, T is equal to T naught at the wall. So, moving forward, so now how do I address this problem? And the hydrodynamic boundary layer is same as what we had dealt with in the past in the integral method. However, the thermal boundary layer starts to develop little later because the heat source is placed little later. So, that is the situation. So, we are going to make a critical assumption that the thickness of the thermal boundary layer is always going to be less than delta, and we will see why that is needed to solve this problem in a fashion. So, moving forward, so this is the situation where the temperature profile develops after the hydrodynamic boundary layer starts. So, we will use the integral method, and in the integral method we need to first find a profile. So, in order to find the profile, we need certain conditions to know what temperature profile will choose. The velocity profile can be same polynomial profile. There are, as you can, this is, we will assume a polynomial profile, not a linear profile like a Couette flow, but we are going to assume a polynomial profile for velocity. And you can see for conditions for developing for temperature profile at y equal to 0, that is at the wall, for x 0 to x less than x naught, there is adiabatic section. This is your adiabatic section we discussed previously, and at is T naught, this is the incoming temperature, T naught is the inlet temperature. And at y equal to 0, after x naught, we have wall temperature prescribed, and this T wall for the sake of discussion is assumed to be T wall is greater than T naught. T naught, T wall can be less than T naught in case of sinking applications, but here we are talking about heating applications or and so at y equal to infinity, that means if you treat this as a semi infinite plate, the temperature beyond the boundary layer is going to be same as the ambient temperature, and you can easily derive the condition that the partial derivative of temperature with respect to y at that point is going to be 0. So, this is sufficient. Once this is specified, then you can also specify d square t by dy square equal to 0 and so on. So, this we call equation number 1, and the energy equation is the typical energy equation that we encounter. This is the advective part of the equation, and this is the diffusive or the conduction part of it. And as you can see, there are 4 terms or 4 conditions that we have. So, we can go ahead and use a polynomial, a third degree polynomial of this form, a plus bx plus cy square plus dy cube. A, B, C, D are constants as we had discussed before, but we are going to set theta equal to, instead of writing in terms of absolute temperature, we are going to write it in the form of theta equal to T minus T wall. T wall, as you know, is constant, and T naught is also a constant. So, theta is nothing but temperature that we do not know yet, and T wall is the wall temperature specified after x greater than x naught, and theta naught is nothing but T naught minus T w. This is theta naught is constant. So, once the temperature profile is chosen, now we can use the boundary conditions or the conditions we discussed in the previous slide, these guys y equal to 0, this and these conditions, and we can arrive at the polynomial. And as you can notice, this polynomial turns out to be same, very much same as what you would have derived for the flat plate case without any unheated starting length. However, the difference will come when we, as we move towards and where we make use of the x naught conditions. So, the y is the vertical coordinate, and on the other hand delta t is the boundary layer that starts to grow after a little while. This is your thermal boundary layer, but this thermal boundary layer is a function of x, because this is your x, and the hydrodynamic boundary layer delta is also a function of x. And y divided, because it is a thermal temperature profile, we make use of the thermal boundary layer thickness, and so y 3 by 2 y by delta t minus 1 by 2 y by delta t cube, and these I have already specified. So, let us move forward and now obtain the same solution, which is same as what you would have encountered in the past. In the past integral method is that y equal to 0 for the momentum or the velocity boundary layer or velocity profile, we use the conditions y equal to, at the wall the velocity is 0, because the plate is assumed to be stationary. So, it is 0, and the derivative, second derivative, partial derivative is also 0. Now, at y tending to infinity, the free stream velocity is encountered. U is the velocity is same as free stream velocity at far away from the boundary layer, and the du by dy, this is not partial, this is ordinary differential, or just the differential of u with respect to y at that is 0, because the velocity is constant there. So, again choosing a third degree polynomial and seeking a solution, you get the same solution you would get for the temperature, and except that the y is now divided by delta. Delta is the velocity boundary layer thickness or the hydrodynamic boundary layer thickness. These are two solutions you would have anyway obtained with the integral method that was discussed in the past. So, until this point there is no big difference. So, now we move to the next part, which is the heat flow equation, which is nothing but this is your theta minus, you can write it in terms of T naught minus T, and then non-dimensionalize it or use T minus Tw minus T minus Tw. So, that is just theta minus theta naught minus theta, and times u dy, and this integrand has the limits of 0 to y. So, if you pull theta naught, which is a constant, and u naught, which is a constant, we substitute for theta naught minus theta and u from the previous derivations, we substitute that over here and we get equation number 5. What we have done is that pull theta naught out of the bracket. So, you will have 1 minus theta divided by theta naught. the theta by theta naught is the value that we have. So, this is the expression for theta divided by theta naught, and we substitute that, and this expression for u by u naught is also substituted, because what we have done is that we have divided u naught and pulled u naught out of it. So, you have theta naught into u naught 1 minus the expression for the theta divided by theta naught, and this is u divided by u naught. This forms our energy equation. We are not going to worry about the shear stress because it is already derived and it will be the same. We will just discuss it very briefly. So, then we are going to make a critical assumption that delta, the thermal boundary layer thickness, is always going to be less than the hydrodynamic boundary layer, and it is quite true for air because we have an unheated starting length, and it may be on the order of same in the case of air, even if the starting length is 0 or the unheated length is 0. So, there is an approximation we are invoking here, but it is still okay because the error associated will be considered to be small and it can be shown to be small. So, we take this assumption and we write R, which is the ratio of thermal boundary layer thickness divided by the divided by the velocity boundary layer or the momentum boundary layer thickness. So, this we write this expression as theta naught u naught into we pull delta, and we write in terms of r square and r power 4. So, what you see is that because we have made the assumption of delta t by del is less than 1. So, this fourth order term can be neglected. So, we will discuss that, and so this is the equation that we can make use. So, we are going to neglect this part on the order of 0. So, this we are going to make use in terms of analyzing is that we are going to use only this term 3 by 20 r square into going forward, and if you use that with the standard function that we know for the integral method is that you have d by dx of t naught minus t times u dy 0 to y is equal to alpha thermal diffusivity and dt by dy at the wall. So, we substitute all the relationship that we have obtained, use theta instead of t and t naught. So, we use t naught minus t wall, t minus t wall, t minus t wall, and substitute the values associated, do the differentiation, and after using that and substituting it, you will end up getting the same 3 by 20 theta naught u naught into d by dx of r square delta equal to the right hand side 3 by 2 alpha theta naught by r delta. So, this after simplification, bringing all the other terms towards the left side and keeping only the thermal diffusivity on the right side, you will get 1 by 10 u naught r cube, because if you do differentiation del into d del by dx plus so on. So, this expression, because r square is also a function of x, because r is nothing but thermal boundary layer thickness, which is a function of x, divided by del, which is a function of x. So, r square needs to be differentiated and the del, which is also a function of x, needs to be differentiated. After you differentiate, you will end up getting this expression. So, making use of this and correcting, we know that from the velocity boundary layer discussions you may have had in the past, the del times del d del is equal to 140 by 13. This is the kinematic viscosity, divided by the velocity, the free stream velocity. This is something you would have derived in the past. So, using that expression and assessing the boundary layer thickness for the momentum boundary layer thickness is 4.64 divided by the square root or multiplied by the square root of mu with kinematic viscosity times x by u naught. This can be rewritten as delta divided by x, 4.64 divided by square root of Reynolds number. This is the hydrodynamic boundary layer theory. On integral method you will achieve this. So, making use of that in the expression for delta in the previously developed expression for delta here. So, we use that, substitute that expression for delta here in expression 8, we achieve this equation. We see that 14 divided by 13 times the Prandtl number shows up here, r cube. R cube is, r is nothing but thermal boundary layer thickness divided by velocity boundary layer times 4x times r square dr by dx equal to 1. If we just try to set this to 1, assuming that approximation is enough, then in order to simplify the situation and we substitute mu by alpha and ignore the property variation as a function of temperature, then we can achieve this equation, which is r cube 4 by 3 x into dr cube by dx. We take this r square and bring it into the differential with respect to x. We can rewrite it as r cube and divide by 3. So, 3 goes here and so on. So, this is the expression, and this is a simpler equation that can be solved using we know this by substitution method. So, we substitute for r cube a function y n and we put that over here. So, you get an expression y n plus 4 by 3 x dy n by dx equal to 1 by Prandtl. So, this expression has a certain particular integral. That particular integral will only be this y n is equal to 1 by p r, and the general solution, as you can see, it has an x term here. So, one can judge that it will be on the order or of the general solution can be obtained by using some x raised to the power polynomial type solution. So, substituting x raised to the power n and realizing that if n is equal to minus 3 by 4, then because it is a homogeneous solution. So, we write y n plus 4 by 3 x into d by dx of y n is equal to 0. So, we know that there is 4 by 3 and there is x here. So, there is y n is the only factor. So, if we use the value of y n equal to x raised to the power minus 3 by 4 d by dx, then you will realize that this term can be used to negate this fellow, and you will get that this is equal to 0. So, a function y n, the homogeneous solution will be minus x by 4. So, this if we substitute, we get the particular solution or the particular integral is here pi, and this is the homogeneous equation part. This is our equation number 12, but we know for x equal to x naught, r equal to 0 or y equal to 0, we get r is equal to 1 by cubic root of pr. So, all we are doing here is that we are just substituting these conditions for y equal to 0, and you remember y power n is nothing but this r raised to the power cube. So, this is nothing but r raised to the power cube. Substituting that, and you will get that at x equal to x naught, r equal to 0 or y equal to 0, that is at the wall, r is nothing but 1 divided by square root of Prandtl number, cubic root of Prandtl number, and this expression shows up. This is just purely obtained from substitution and cubic root scenario. If x is not equal to 0, this is the final expression that one would say. So, if x naught is equal to 0, that means if I do not have a starting length, if my boundary layer both are developing from the beginning, it boils down to r thermal boundary layer thickness divided by the delta is seen to be cubic root of Prandtl number. as you can see, this is some kind of, there is an error associated with this assumption, but luckily for air it is on the order of 0.7, and for most gases Prandtl number is on the order of 0.6. So, for gases one may be able to use this expression even though there is an error associated with it, but the error is expected to be small. So, we will still hold this assumption of delta T by del. However, this assumption is invalid if we are talking about Prandtl numbers which are much less than 1 in the case of metals, molten metals. So, for Prandtl number greater than 1, which is like viscous oils, this expression holds true and there is no issue, and we can use it as accurately as we want. Then moving on is that next order of business is to find out, we know we have now obtained a expression for R. Now we need to use that in terms of finding the heat transfer coefficient, which is our ultimate objective, is using the Q flux or the Q double prime, which is the heat flux, is equal to minus K d theta by dy at the wall. This is at the wall, and as you know, we have already calculated this theta function from the velocity temperature profile, and this is nothing but if heat transfer coefficient using the Newton's law of cooling, T naught minus T wall. T naught is the ambient temperature or the free stream temperature, and T wall is the temperature that occurs after x greater than x naught. So, because at the section where 0 x less than x naught, T is equal to T naught. So, there is no heat transfer coefficient, only heat transfer coefficient starts to develop after x greater than x naught. So, substituting the profile and calculating it, we get an expression for heat transfer coefficient as 3 by 2 K divided by R and delta. Delta we already discussed previously, delta by x was equal to 4.64 by square root of Rex. R we just got the value in the previous expression, R was cubic root of Prandtl number raised to the power 3. This expression. So, using these two expressions in here and trying to get a heat transfer coefficient, we end up getting a nice expression of delta, substituting for delta, and you get my apologies, we need to use equation number 13, not 14, because 14 was obtained when x naught was set to equal to 0. So, we use R and in this expression. So, if you use R in this expression and equation 13 and delta expression in here. So, we get a heat transfer coefficient that is 0.332 K into square cubic root of Prandtl number divided by cubic root of 1 minus x naught by this. And this, if we recast it in terms of Reynolds number, this can be done in terms of Hx and K. We get the Reynolds number square 0.3 and this and this. And as you can see very easily that setting x naught equal to 0, which is the case where we have both boundary layers starting from the beginning, and it is a isothermal temperature case T equal to T wall right from the beginning with the inlet. So, we recover the Blasius solution or the integral case. This is case when x naught is equal to 0. So, the only change that has happened with unheated starting length is that you have a delayed beginning and there is an associated change in the NUX behavior. So, this is the unheated starting length, and what we have achieved is that now we have an expression very similar to the expression where the boundary layer starts from the leading edge itself. However, you have a change which is cubic root of 1 minus x naught divided by x raised to the power 3 by 4. So, if we move forward, but we are always interested in knowing the average heat transfer coefficient, which is what is the average heat transfer coefficient is nothing but, average is nothing but, or the mean heat transfer coefficient is 0 to x h dx and if we collect all the terms that are independent of x and cast it as as C, like Prandtl number and so on, and keep this, and we see that you get an expression for average heat transfer coefficient to be 2H. So, the same relationship can be used where 0.332 times 2 will fetch you the, which is 0.664. Coefficient is the only change that will occur, and we can use the expression developed here. So, how to use this for the case where there is adiabatic region, then there is constant wall region, again some adiabatic region, constant temperature and so on. So, if we have such a situation, because the energy equation is linear, this energy equation is linear in nature, and we can, once the linearity is known, we can make use of the superposition method to obtain this. So, what is superposition method is that we develop solutions for unit disturbance. This is the disturbance solution that we obtained, and we can superimpose other solutions, and if this is adiabatic region, we can switch it off, and so you can get, if it is a continuously heating and increasing temperature or so, you can easily put step functions and add the solutions one by one. For each region, S1 region you get a solution, S2 region you get another solution, S1 to S2 and so on, and add them linearly. So, once you get that linear solution superposed, then one can easily obtain, and you, in the case of arbitrarily varying temperature along the wall, you can easily get the same expression that we have developed previously, and just use an integrand and a summation and an integrand, and obtain a final solution for any degree of variation, and that is useful in the forthcoming situations where we will discuss. And we will not develop this part, the arbitrarily varying solution, but we will make use of this discussion in the future.